Well, welcome to day 2 on natural log integration, and yesterday we introduced you to a new antiderivative. We said if we could rewrite our integral in the form of du over u, then the antiderivative is going to be the natural log of the absolute value of u plus c. Well, today we're going to introduce you to some real angry, nasty bear of a problems, and hopefully by the time we flex our math muscle, we're going to turn them into this. You got it. Nice warm teddy bear. So by the time, they're going to appear pretty nasty and they're going to be overwhelming at times, but we're going to stick to our guns and we're going to go step by step and we're going to stay on our toes, and by the time we're all done, we're going to look back and really turn it into a tame teddy bear. All right, we're going to jump right into it. I'm going to jump right into a pretty hard one. I think we did really well with the basic, the medium to slightly above medium problems today, so we're going to get right after it with a nice hard one. So I want you to look at this integral here we've got, and specifically I've asked you to really look at the powers. Look at the powers. We said yesterday if you're integrating a fraction, I want you to instantly let u equal the denominator and see where that takes you. But I think you could quickly visualize if right now I let u equal the denominator, what's going to happen is I've got a du of 2x, and I'm not going to be able to cancel all the x's that are sitting up here in this numerator simply with this little x right there. So we've got a problem. I'm not able to kill all the x's. So we said look at the powers. Well, our biggest power on top is a squared. Our biggest power on the bottom is a squared. And so we would say that the degree of the numerator is a 2, just because it's the biggest exponent, and the degree of the denominator is a 2. Again, biggest exponent. So here's this rule we have. And this is going to make you cringe, so I want you to brace yourself. Make sure you're sitting down for this. If the degree of the numerator is greater than or equal to, and in this case we've got the equal to case, the degree of the denominator, we must first perform, hold yourself, log division. Okay? And I know some of you have probably broken into tears, perhaps sobbing right now, but I'm going to tell you right now it's going to be okay. We're going to get through it. All right, so we've said we've got to get ourselves into long division because letting u equal the denominator did not successfully cancel all the x's in the numerator. The numerator is too big, the numerator is too powerful. I've got to take a different technique. So what I want to do is I'm trying to find an equivalent expression. Okay, I'm trying to find an equivalent expression that I could eventually substitute in this guy's place right here. So I'm going to go ahead and I'm going to set up my long division here. And I know, we've been exposed to this. We're probably a little rusty. That's okay. We're going to do a little quick refresher here and just all get on the same page. As you're doing long division, you want to keep your focus on the leading terms. Okay? Our leading term in the divisor is x squared, and our leading term on the inside is x squared. And you want to ask yourself, how many times does x squared divide into x squared? The answer to that is once. Notice where I put the 1. I want to line it up so that everything is strategically lined up with like terms all falling in a certain column. What I'm going to do now is I'm going to multiply the 1 through, I'm going to distribute it through the divisor, and that's going to give me, let's see, x squared plus 1. Okay, and again, I'm lining everything up very strategically in columns. What I'm going to do is I'm going to wrap up that expression and I'm going to subtract it. So we've got, x squared minus x squared is 0, plus the x, and again, the 1 minus 1 is, again, 0. All right, and this was a really easy one to start off with because I'm pretty much done right now. The reason I know I'm done is because the degree of what's now left is smaller than the degree of the divisor, and so I've gone far enough, I'm done. And what I have here is the remainder, basically. I'm going to say plus x all over the divisor, x squared plus 1. And this, ladies and gentlemen, is my quotient. Alright, that's the answer to our division problem. So here, what are we really saying here? Let's see, let's not lose sight of what we're really trying to say. So we started off with a fraction of x squared plus x plus 1 all over x squared plus 1. And we're now trying to tell you that it's equivalent to 1 plus x over x squared plus 1. Again, there's your quotient. So, rather than integrating this rascal where u sub doesn't work, we could integrate an equivalent expression in its place. So we're going to focus on this integral right here. According to my properties, I'm allowed to rewrite the integral as two separate ones. I could integrate the 1 with respect to x, and then we could integrate the x over x squared plus 1 with respect to x. The first integral, well, why don't we split this in half, okay? 50-50. I'll take the one on the left, okay? I'll let you guys take the one on the right. They're about the same difficulty. Okay, go. Well, obviously, I got the better end of that deal. My integral was simply x. And in order to finish off your integral, I believe that you guys are going to have to do some u subbing. I think we're going to let u equal the denominator, just like we did last night. The derivative is going to be 2x dx. And of course, we'll solve for dx. And I'm now integrating x over u times du over 2x. Cancel those x's, pull out your coefficient, and let's get ready to finish this one off. So we bring down that x plus 1/2, and again I've got my du over u, so it's the natural log of the absolute value of u, which in this case I'm going to rewrite it in terms of x right away, plus c. Ladies and gentlemen, here we have it. There's my antiderivative. And the big key to this one, I don't think the calculus was too difficult. Really, everything hinges on our ability to do the long division. First of all, recognize when to do it, and then to be able to execute it. All right, we're going to try one more feistier one with our long division. X cubed minus 3x squared plus 4x minus 9. Quite the numerator, huh? X squared plus 3. Again, I want to encourage you here, with just a little bit of practice, I think you're really going to gain a lot of confidence with your long division, and you're going to be able to rock and roll. First of all, what's your trigger? If I'm in the middle of a test, how am I even going to recognize the need for long division? How am I even going to know that I need to do it? Well, compare the degree of your numerator to the degree of your denominator. I've got a third degree numerator, compared that to a second degree denominator. And remember, we said if the numerator is greater than or equal to the denominator, we're going to have to do long division first, because there's no u sub that's going to be able to cancel all my x's. So I'm going to go ahead and I'm going to set this up. I've got x squared plus 3 as my divisor, and I've got this extremely long numerator right here. And all I'm trying to do is I'm trying to determine what is the quotient. And, I want to replace this big, ugly thing with something more manageable as far as integrating goes. Again, focus on your leading terms. How many times, let me say it this way. What's x cubed divided by x squared? Hopefully you said x. We're going to line everything up really nice and neat. Take this x, distribute it through your divisor. That's going to give you x cubed and plus 3x. I'm going to wrap up that expression, and I'm going to subtract. We're really distributing that negative sign through, if that helps. I don't know if that helps. Maybe you could write it like that. You'll see the x cubes cancel. You still have a negative 3x squared. We have a 1x, and we'll bring down the remaining terms. Is there more work to be done? Yes, there is. And here's what I'm going to say. Let's see, ask yourselves, what's negative 3x squared divided by x squared? And the answer is negative 3. Distribute your negative 3 through the divisor, and we will get this. Wrap that expression up. We're going to subtract. You can go ahead and distribute your negative if you feel better about that. And the 3x squareds cancel. We get a plus x, and then the 9's cancel. How do you know you're done? Well, the degree of this term is smaller than the degree of your divisor, so you are done. You've identified your remainder here, so we've got x all over x squared plus 3. Ladies and gentlemen, this is your quotient, and that's what you're now going to integrate, because it's equivalent to the fraction we started with. So how are we going to write this? Let's rewrite our integral. All right, we're really integrating. All right, x minus 3 plus x over x squared plus 3. I'm going to rewrite it as 3 separate fractions. I certainly do not need a u sub on the first 2 terms. Those are very simple terms, but I am going to use a u sub on that third one. I'm going to go ahead and get that part out of the way right now. I'm going to let u equal the denominator, and my du is going to be 2x dx. Solve for dx again. We're very good at this right now. And let's go ahead and finish off this integral. Let's see, the first term is going to be 1/2. Oops, grab the pen. There we go. 1/2 x squared minus 3x, and the last one, I'm still going to write it as an integral. I've got x all over u and du all over 2x. Kill those x's, pull out the coefficient, stay organized, stay crisp and clean. Don't let yourself make any careless mistakes right here. And the antiderivative is going to be the natural log of u. And we got a little plus c. So there it is, ladies and gentlemen. There's a one big antiderivative. Alright, we're done with long division for the night, so that's the good news. We'll probably have 2 or 3 in class tomorrow to practice on. And but I am going to introduce you to another grizzly here, and just a complete change of variables. When we talk about complete change of variables, continue to preach to yourself that everything must be rewritten in terms of u. We've got to get all those x's to cancel, and we've got to adjust the bounds if it happens to be a definite integral. But I want you to look at this problem here. Let's talk about 2x all over the quantity x plus 1 squared. Now, there is no need for long division because the degree of my denominator is greater than the numerator, so you can take a sigh of relief there. And we are going to let's see, and this kind of comes with experience. I'm going to go ahead and let u equal the inner function of the denominator and see if that takes me anywhere. We may hit a dead end and come on back and change our mind. But typically, when you're deriving the u, and we've seen this in class the last couple of days, if you're using chain rule or product rule or quotient rule to derive your little u right here, then that's probably a bad sign. That means you probably bit off more than you wanted to chew with your u statement. So I'm going to go back and I'm going to substitute back in, and I've got 2x all over u squared, and I'm going to substitute the du in for dx. Do you like what you see? Do you like what you see? Well, I'll tell you what, I don't, because I was not able to cancel all the x's. Okay, I still got this x dangling in there, and that's a major problem because everything's got to be in terms of u. So what I'm going to do is I'm going to go back to this statement right here, and I'm going to solve it for x. I'm going to say u minus 1 has to equal x, and I'm going to substitute the u minus 1 in for this x right here. Alright, so we've got the integral of 2 times the quantity, u minus 1, all over u squared. Alright, we're going to use just some real basic techniques to rewrite this. And let's see, the numerator is really 2u minus 2 all over u squared. I could have pulled the 2 out in front of the integral, I guess, if I wanted to. I'm now going to make like a beaver and split it up. So I've got 2u over u squared minus 2 over u squared. And I'm going to rewrite this in the friendliest form, knowing that I'm going to have to integrate. So the first term, I'm going to cancel the u's. First of all, I'm going to pull the 2 out, and I'm going to go 1 over u minus, and let's see, I'm sorry, I hope this isn't confusing. I'm going to set up a second integral for this term. I'm going to pull out the 2, and I'm going to rewrite that one as u to the negative 2. Now, you're asking yourself, why in the world would you leave the first one as a fraction, but rewrite the second one in terms of a negative exponent? Well, the bottom line is, it's all about writing the question in the form that makes it the easiest to integrate, okay? So on this first term, you quickly recognize that we do have a du over u. So the antiderivative is simply the natural log of u. But on the second term, we don't have du over u. We're going back to the old power rule, where we're going to add 1 to the exponent, and then we're going to divide by the new exponent, thus making this a positive 2. Then we'll throw on our plus c. We'll rewrite everything in terms of x. And going back to the original problem, I believe x plus 1 was our u, and we've got 2 all over x plus 1 plus c. So what I really want to stress here is understanding why I left the first one as a fraction, but I rewrote the second one in terms of a negative exponent. I think that's a big key to pick up. Alright, our last example tonight, I want to do one more example, kind of similar to the last one, where I'm not going to let u equal the entire denominator. Okay, pretty much up till now, that's how we've handled this. We've always said if you're integrating a fraction, let u equal the denominator. Well, here's another example where I've got to finesse it a little bit more. I've got to be a little more creative. Okay, and again, this just comes with practice. So let's talk about 1 over x times the natural log of x. My first clue is, how come I'm not going to let u equal the entire denominator like that? What's my first indication that that's probably not a smart move? My first inclination is the fact that the derivative would require a product rule. And as I've mentioned before, that's typically a bad sign. So what I'm going to do, and again, this comes with a little bit of creativity. Maybe we try, there's going to be times where you pick a u and it's wrong, and it's okay. You may work through it a little bit and hit a dead end and come on back. I'm going to let u equal the natural log of x only. And I'm going to see where this takes me. The derivative of u is 1 over x times dx. By the time I solve for dx, I get x times du equals dx. And this is the substitution that I'm going to make. So as I rewrite my integral, it's going to be 1 over x times u, and then x times du, basically all over 1 if you want. You know, that's over 1. So now you can see that, yes, the x's do cancel. I've successfully eliminated all the x's. I'm integrating just du over u. At this moment, we can kind of start to celebrate because you can see how things are falling into place. And the last thing I'm going to do is I'm going to substitute back in for u. U happen to be the natural log of x, so that's kind of exciting. So our antiderivative is the natural log of the natural log of x plus c. Kind of exciting. So good luck tomorrow, and we'll see you.